Good morning, good afternoon, good evening, everyone. Thank you for your time today. Today's topic is next generation lightweighting with improved NVH. We are trying to, this webinar is in the efforts of providing the solutions to our customers and providing new workflows and ideas on how they can do their day-to-day work and make their life easier. So today's presenters are myself, Bhumi Gadia, Product Marketing Manager for MSC Nastran and Mark, and Homa Boston, he's a Product Marketing Manager for Actron. And we're going to show you more of the workflow to make your life easier. So before I get started, I would like to get over a few technical details of the webinar itself. We will have 45 minutes to present this webinar, and we'll save about 10 minutes at the end of the hour for questions and answers. So if you have any questions, please type them in the Q&A panel during the presentation itself, and we will read these questions out loud and answer them in the last 10 minutes. In the chat panel, if you have any difficulties viewing the screen or with the audio or anything, please let us know, and we can help you out from here. So let's get started. Today's agenda is we'll go through some automotive market trends. Then next we'll go through some industry pain points, which we have realized working with our customers. And we'll also show some existing methods and how everybody is doing it today. Then we will propose why MSC and which MSC solutions slash workflow are going to fit into this particular topic. And then we have worked with our customer in this to develop this workflow, so we'll talk more about that, and we'll give you some more examples on that as well, and then we'll conclude this webinar. So let's get started. I'll hand it over to Homa to present the automotive market trends.
Thank you very much, Bhumi. I hope you can hear me. Yeah, so good morning, good afternoon, everyone. Thanks for joining this webinar. So yeah, we wanted to start this webinar by looking at some automotive market trends and how they are basically linked to lightweighting. So if we move to the next slide and look at actually what are those market trends, well, we can basically highlight 5 main topics. Of course, we talk a lot about electrification, autonomous driving, car as a service, connected vehicle, and finally lightweighting, which is the main topic of today. What is interesting is to understand how those different trends are connected, and actually they are strongly interconnected. And also driven by some main drivers, in particular regulation, economical driver, and consumer aspiration. So if we try to map those drivers on the different topic, well, electrification is actually mainly driven by regulations. We know that we do have CO2 emissions regulation all over the world, and electrification is a solution to achieve those regulations. When it comes to autonomous driving, connected vehicle, and car as a service, well, aspiration is very important. And so today we'll talk about lightweighting, which is somehow slightly separated, but impacts all of those trends. So yeah, what about lightweighting? If we move to the next slide, we know that lightweighting, and in particular weight, has a direct impact on the electric vehicles range. This is reflected on the 2 figures you can see at the bottom of this slide, where we are comparing the range of different batteries versus the vehicle weight, so the energy consumption versus the total mass of the vehicle. But what is interesting is to look at the top graph on this slide, where we see, following a survey that has been conducted, well, what we can look at is the 3 main barriers to the adoption of electrical vehicle. The very first one is charging limits. We know that it will be overpassed in a few years. The last one is the high price that we still have for electrical vehicle. But if we look at the second one, it's the range limit. So we know that if we work on improving the range limits of current electrical vehicle, which means reducing the weight of those electrical vehicles, we will fasten the adoption of electrical vehicle. Having said that, well, we can move to the next slide, where this time we look at the link in between the vehicle mass, the reduction of the CO2 emission. And again, if we are able to reduce the mass of the vehicle, well, we know that, as we just said, we will extend the range of electric vehicles, so we'll faster the EV adoption by the consumers to finally reach our goal to reduce the CO2 emission. On the other hand, if we look at classical internal combustion engine vehicle, well, we know that reducing the mass will, at the end, lower the fuel consumption of those vehicles, so that we will reduce the CO2 emission. So reducing the mass of the vehicle has a direct impact on CO2 emission if we talk about electric vehicle or classical internal combustion engine. What is interesting is actually to look at the trend and to ask this question, but are our car really getting lighter? And what we see on this slide, it's totally the opposite. Here we try to illustrate the evolution of typical vehicle we can find on the market, both in terms of evolution or surface area evolution. And we see that for any type of vehicle, well, both the surface of the vehicle and the mass is increasing. And of course, this is mainly due to the fact that if we look at what are the top selling cars actually on the market, we know it's mainly SUVs. So on the next slide, we are somehow reflecting this consumer aspiration. So just some figures on the top selling vehicle that we had in 2018. And we know that there is this global consumer favor for SUVs. If we put in parallel the other figure we have on this slide, where we highlight, well, the evolution of all passenger cars weight versus engine power, engine displacement, and CO2 emission, we clearly see that there's been a lot of improvement achieved by the different OEMs in the past, because we do have a weight increase because of the size of the vehicle, but at the same time, OEMs were able to achieve CO2 reduction as well as engine power increase. So it means that we can achieve better performances if we are able to contain the weight of our vehicle. Now, actually, the way to reduce the weight of a vehicle is by introducing new materials. So moving to the next slide, we know that definitely the most common way of removing mass without actually compromising the design is by introducing new materials. Here we do have graphs highlighting those trends of new material that are introduced within our vehicle. What is very interesting is to look at the bottom left picture, where we see some projection of the different material that will be used in the US fleet. And if we look really at the end of those projections in 2040, we see that basically the mild steel will only be about like 5% 5% distribution over the different material, and we see more and more composite material as a different type of aluminum that will be used. So, of course, introducing new material will have a direct impact on the NVH performances of our vehicle. I think this is highlighted in the next bullet on this slide. Basically, because it has an impact, well, now we need to understand is lightweighting achievable. And I think, yeah, Bhumi.
Yeah, okay, so the real question, like Homa talked about all the trends and everything, but is lightweighting really achievable? So we're going to talk about that in this slide. So as Homa mentioned, we will talk about some industry pain points that we have noticed in the market right now. There are some government regulations for higher fuel efficiency that are put into place and the consumer demands for safety and comfort, as well as there is a global demand for lightweighting materials. This drives the automotive industry to accelerate the innovation and focus on composites. Adding new materials and adding new composites adds new challenges for the design step to manufacturing step. And the main challenge is that in reinforced plastics, the microstructure shows only high degree anisotropy in terms of stiffness and damping. So it's very difficult to capture the correct local anisotropic behavior of the material, and only a material model based on matrix and fiber properties that that takes into account the fiber orientation distribution throughout the part. That can accurately predict the stiffness and damping behavior of the materials. So we'll talk about existing methods for NVH. The method one is where the data for isotropic homogeneous modeling is obtained from a material supplier, and then the E-modules and damping factors used in NVH studies with FEA are obtained from the supplier. And this is fast and easy day for the user, and there is no further need for investigations in this case. But the cons of this method is it makes kind of like a black box, so no information is given about the origin of the value, and there is no association between provided data and the fiber orientation. So there is a lack of accuracy in this case, we have seen in some cases. So the frequency results are off by a minimum of 10% in average. So although the 10% may be good for many applications. For frequencies, we generally manage to be very accurate within 1 or 2% error. Explorations are off since damping is very highly frequency dependent and related to fiber orientation distribution. The second method that we've noticed is a user obtains the isotropic homogeneous model parameters through investigations. The stiffness and damping values are obtained from the data sheet information and a set of experimental data. This is usually measured at a component level, and then it's taken on. Damping and stiffness values are scaled to minimize the gap between simulation and experiment for identification of frequencies and acceleration. So this method is good, and the OEMs can be more confident in the modeling approach as it's obtained from internal investigations. But the cons of this are, again, we're unable to understand the influence of local fiber orientations on the material's anisotropic stiffness and damping values. There is also lack of robustness. So the identified model is highly linked to the component, injection settings, and the load cases used for component testing. So for example, for the same shape, same load case, but different injection settings, the component behavior will change due to the change in fiber orientation distribution. So this cannot be captured by the homogeneous isotropic model identified with this method, as no links exist between the model behavior and the fiber orientation. So what is needed in order to give an accurate prediction? So a complete end-to-end solution with advanced material modeling to NVH studies to acoustic simulations is needed. A multidisciplinary FEA solver for vibration analysis, and then incorporation of both anisotropic material properties and the manufacturing processes using a material management tool is needed. And then this improves the accuracy it gives improved accuracy to the engineers and more confidence when making decisions. So we're proposing complete end-to-end NVH process. This was a project done with Ford Motor Company, and we did work with their oil pan, and they use glass fiber reinforced plastic materials for powertrain parts, such as engine covers, air intakes, and engine oil pans. So the first step is to obtain a better understanding of material characterization on samples applied to the engine oil pan model, and then next is generating material models in Digimat. to gain better understanding of microstructure. And then the third step is to perform vibration studies in MSC Nastran and obtain a structural response. And then the fourth and last step is to obtain the acoustic response in Nastran. So the first step is testing where we characterize the anisotropic and damping of the sample as a function of frequency and fiber orientation. Tensile and DMA, which is the dynamic mechanical analysis test on samples cut from injected plaques to measure stress and strain are done. And then by doing this, we have gotten the stiffness and damping. Two fiber orientations were used in the samples, injection flow direction 0 degrees and injection cross flow direction 90 degrees. And then the component testing on the oil pan was done. So they conducted a hammer test to measure frequency response characteristics of the component, and the oil pan has been submitting to a drying procedure to make material in coherent conditions compared to one tested on the samples. A free condition without oil in the pan was tested in this case. Next, we took the input from the DMA test, and those are sent to Digimat. Digimat takes input in 0 degree and 90 degree for stiffness and damping values for this case to create a material model with correct material properties that are the function of the fiber orientation and frequencies. In parallel, comparing the Digimat model to DMA test data, the model provides correct material properties. So here the red shows the experiment and the black shows the Digimat data, as you can see in the graph. So 0 degree measurements, both shear stiffness and the delta at 0 degree are perfectly captured. And then at 90 degree measurements, the gap on shear stiffness is less than 5%, and the gap on the delta is 0.0003 here. So next, we look at the anisotropic material modeling. Here, we perform an injection simulation model of engine oil pan to predict the fiber orientation distribution inside Digimat. So fiber orientation tensor coefficient is shown as A11. The 11 stands for X direction, and then the color indicates the orientation intensity in given direction, which is here it's X direction. So once the fiber orientations have been predicted from the injection molding simulation, we map the frequency-dependent stiffness and damping properties onto MSC Nastran mesh and generate the MSC Nastran model scenario in the next step. So here we're doing the model preparation for Nastran to study the vibration response of the part using the frequency response analysis in solution 111 to obtain both modal response and acceleration response of the component. We have 3 sample models of the oil pan. Force response analysis using a unit load is applied at 3 specific locations of the component. We define the mesh geometry, defined loads and boundary conditions, and then the simulation is based on the free boundary conditions in the study for the oil pan component. Material data are mapped into MSC Nastran model based on the orientation of the fibers, which was taken from Digimat. We used the new MAT-F entry in MSC Nastran, which allows to easily and accurately account for effects of fiber orientations and frequency-dependent materials obtained from Digimat. So it's a direct and easy transition from Digimat to MSC Nastran. And we compare the vibration results of MSC Nastran with both isotropic and anisotropic modeling. The multi-scale material modeling helps correctly capture the behavior of SFRP materials, and the overall accuracy is significantly improved with the anisotropic model capturing peak responses for both eigenfrequencies and acceleration results, as you can see in the graph over here. So next we will, and then after this, the oil pan sound radiation was performed, but we can perform that. So I will let Homa as an expert to talk a little bit about that, and then he will go through more examples as well. Homa?
Thank you. Sorry, Bumi. Yeah, indeed. So process is quite straightforward. I mean, as soon as you do have structural vibration obtained in MSC Nastran, you can easily move to Actron to perform acoustic radiation, and actually your acoustic model is set up automatically, meaning that based on the structural mesh, well, the acoustic mesh around the structure is generated automatically, and structural results are used as a boundary condition in the acoustic model to perform an acoustic radiation in simple environment or more complex environment. So indeed, we created other examples just to illustrate that this process can be used for actually lots of parts of the vehicle. Here in this example, well, we used air intake manifolds of a vehicle where, again, we did create an MSC Nastran finite element shell model of the air intake manifolds structure. We did apply multiple excitations on the different attachment points to represent some engine order excitation. And at the end, we will look at acoustic radiation in free fields. In this case, we are interested in performing a parametric analysis over 5 different plastic materials by changing what we call the density of the fiber. So first we will look at isotropic result, which is somehow reflecting the typical process. So we get some isotropic value of our material, and then we will add the Digimat information by considering how this plastic piece is actually manufactured and what's the impact on the final structural behavior to finally the acoustic radiation performances. So if we move to the next slide, we are again highlighting the workflow. So here again, the idea is to start from generating material models. Then once we have those information, we can map them on the piece we are interested in, considering the manufacturing process, to finally move to Nastran to perform the structural analysis. And once we do have vibration information, well, we can move to Actron to perform the acoustic radiation. So on the next slide, we are highlighting well, the Digimat process. As you can see on the right hand side of the slide, where we are simulating the injection process. And by that, well, what we can retrieve in terms of information is, for instance, the fiber orientation on our structure. This is what you see on the left hand side. And as you can see, well, there is a non-homogeneous fiber orientation in our, meaning that depending on where we are on our part, well, the stiffness and the damping are actually not the same. So at the end, thanks to Digimat, what we retrieve is really anisotropic stiffness and damping information due to the fiber-dependent material properties. Those information are then mapped into a Nastran model to perform the structural analysis and the acoustic radiation at the end. Here what we are looking at is a first comparison in between the classical approach, so where we do a isotropic material information versus a first anisotropic study for the same fiber density of 50%. And what we clearly see on this first response is the strong impact of considering anisotropic material property on the acoustic radiation power that we look at. So on the right top, we look at the radiated acoustic power. So the blue curve is the isotropic response and the red one is the anisotropic one. So we see a shift in the mode, which is typically what we can expect as soon as we introduce anisotropic, so more precise behavior of the structure. We simply shift the structural response, and this is reflected in the vibration and finally on the acoustic response as well. Moving to the next slide, well, we perform the parametric study. So we are simulating the injection process, but with different percentage of fibers. And here again, we can see a huge dependency of our response on the fiber density. In particular, we see that as the fiber mass fraction is decreasing, we see of the structure that are shifting to lower frequency. And this is directly reflected on the radiated acoustic.
Okay, thank you, Humar. We address all of these industry pain points by adopting this workflow. And since Digimat, Actron, and MSC Nastran are all in MSC One, and they are MSC products, we can do better integration from one product to another, like easy transition, so the users don't spend too much time on transferring the model from material management model to MSC Nastran for FEA and to acoustics in Actron. Here we have addressed that we understand that application of composite material is very essential for weight reduction. Using new materials may come with some level of degradation in NVH performance, and it is generally difficult to capture local anisotropic stiffness and damping behavior depending on frequency and local fiber orientation. So as I said earlier, we will complete with YMSC. We provide a complete end-to-end solution for advanced material capturing to NVH simulation. As we're advancing and going towards more lightweighting materials, it is very important to adopt to new workflows and new technologies. So this gives, this improves accuracy and gives engineers more confidence in making the decisions. MSC Nastran, as we know, is the industry-leading tool for vibration analysis. Digimat helps incorporate both the anisotropic material properties and the manufacturing processes. Noise radiation is computed with Actron with minimal user intervention. This is completely automated process, and it accounts for a complex acoustic environment as well. Here is what our friends from Ford have to say. They used MSC Nastran and Digimat, and that allowed them to optimize the microstructure of composite materials. They're basically very pleased. They did this whole project with us, and they're adopting this workflow for their other analysis as well, other sectors as well, basically. One of the questions in the poll questions is MSC One. MSC One is basically our solution to provide access to all MSC products to our users. So MSC One, if you should ask your manager or your boss, do we have MSC One licensing tokens? If we do, then you have access to Digimat, MSC Nastran, Actron, all three products. So if you are using one of the three products and you want to try out the other product to try out this workflow, you can easily try this workflow with your current license and everything. So you don't have to necessarily reach out and stuff like that. So yeah, so as we said earlier, Digimat helps calibrate physical material properties. It creates fiber orientation dependent material models. Then MSC Nastran does the modal analysis, frequency response analysis, and it does the validation of the results. And last but not the least, Actron uses the vibration results from MSC Nastran as an input for identification of noise levels. Just a last slide to kind of show which areas MSC products are covered. We cover in all of the areas, starting from manufacturing, body and interior, autonomous driving, durability and NVH, chassis and vehicle dynamics, powertrain, and material modeling. So it completes the simulation process and data management cycle for our customers. So in summary, MSC provides end-to-end process from advanced material modeling to vibration analysis to noise studies. And at MSC, we offer both technology and services that can help you. So get started, get trained, and solve the problem. So this is the end to our presentation today. If you have any questions, please type them in the Q&A panel, and we will address them right now.